Welcome back to one more lecture on Introduction to Soft Matter. Last time we were discussing the specific case of the generalization to n Maxwell models in parallel, and we had left off where we had discussed that the force balance equation would look very similar to what we had before, and we had also remarked that the geometry constraint remains identical to what it would remain in the case of elements in parallel, which is something that you would expect obviously. And then we had also remarked that for each of the individual elements, the original equation that we had derived, that still holds, given that you are using the right force on the in this particular equation and the right the corresponding deformation in the body. So, let us try to see how we can solve this set of equations. Okay. So, I am just going to rewrite this, and I am going to say that this basically corresponds to the set of differential equations such that you have so this is for the first element, then you have one for the second element. I am just expanding the equation that I wrote before. Okay. So, this process will go on till I start writing the equation for the nth element. Right. So, we had said capital N number of elements are there. So, here the last term looks something like this. Sorry, this is not small n, this is capital N. Okay. Okay. So, these are the set of equations. So, you have n equations that we have written. Now, from the geometry constraint, we had said that the deformations are going to be the same in all cases. So, what we can do is we can just delete this, we can drop this subscript from all these different terms, right, because they are all the same. So, I am just going to do that, I am just going to go on and delete all the different subscripts. But for the force, the subscripts cannot be dropped, right. So, I have to figure out some other way in which has to be figured out, and the way to do this would be I want to add all the different forces, right. So, I just want the same multiplier with all of them, but the multipliers are different. So, I can resolve this problem by multiplying both sides of these two equations by this combination. So, see you already have d by E2. So, I am going to multiply this with a set such that terms here and you multiply both sides of this equation. Okay. So, I am writing it only on one side, but it is implied that it is also on this side. Right. Basically, this multiplier is something that we have to multiply both sides of the equation here. Right. So, similarly, what do you do for equation 2? Equation 2, you already have this E2, right. So, you start with then the term d E1, and then you drop the second term. So, you multiply it with 3 and like this, and you keep on going till you reach the nth multiplier, and you then multiply this entire equation with that. So, similarly, by the time you reach the nth equation, what you are going to have is you are going to multiply it with 1, and this will keep on going, but here you will stop at the n minus 1th multiplier. Right. And in this, please remember that because the equations are so cumbersome, I am not writing this multiplier on both sides, but they are on both sides. Okay. So, when you multiply this, you will finally end up with the same multiplier for all the f, okay. And that multiplier would be, so I am adding all these different terms here, and what I will end up having is and this dot 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 signifies that all the other terms are there, and this goes on till n number of terms, and then we have f. So, all this will add up and this will give me f, and on this side you will have a lot of different terms. Okay. Now, what you will end up having is you are going to multiply every delta x with some d and this kind of multiplier. D is an operator, but when you are factoring when you are multiplying this, you can also use it as almost as if it were an algebraic quantity. So, you will see that what will happen is for delta x, you will have all the quantities or the terms here will be such that there will be powers of d. Okay. So, this with different coefficients. So, what you will end up having is a polynomial in d such that where q1 qi's are constants, some constants which have to be determined, right. So, you can do this cumbersome addition and you can determine these constants. So, these constants are fully determined, but we are not working it out here. Okay. So, this suggests a constitutive equation of the form d by E1 is 1 by 1 multiplied with all these different multipliers till the nth multiplier sigma equal to this q1 d plus, and this goes on. There are again n terms here, sorry, this delta x will now be replaced with epsilon. Okay. Now, note one thing, that this system here, this will also result in powers of n, powers of d all the way till n, but it will, this polynomial will also have a constant term. Okay. So, this is also effectively a polynomial in for the operator d, okay, with the highest power being n, capital N again in this case. So, the highest powers on both sides for the operator d are the same. So, what we can say is that this is actually some polynomial p of d, and this is some polynomial q. Okay. So, this is sort of an abbreviation for this entire polynomial, okay. And this set of equations is usually written as, so usually we say written in short form as a polynomial in d, in the operator d, multiplied by sigma into a polynomial of which q represents a polynomial in d for the for your right hand side, multiplied by epsilon. Okay. So, this is interesting, and now you can probably see the logic behind why we were writing some of the equations earlier in this particular form. Remember, we were trying to always write it in some P0, P1, P2, and the rationale for that is because once you generalize this, basically you end up having a polynomial on this side and a polynomial on the other side. What the polynomials will look like depends on the particular model. Whether the powers are will be the same is not guaranteed. It again depends on the particular model that you choose. Whether or not there will be a constant term also will again depend on the particular model. So, in this particular case, for the n Maxwell model, we have a situation where we have polynomials in D on both sides, whereas and the powers are exactly the same. That was not the case, if you recall, for the Jeffreys fluid, where you had a mismatch in the higher powers in the powers of operator D in the two cases. Okay. So now let us try to take some special cases. So, let us analyze this further. So, this entire n Maxwell model is going to behave as if this is appropriate for a viscoelastic fluid, right. But what happens? So, this is, by the way, so maybe I will just make a note here. I think I said that last time, appropriate for viscoelastic fluids. Special cases. So, what if you want to, okay, I will just quickly go back to the diagram. So, if you want to have a solid like response, what would you do here? One thing you could do is take, for example, the last or any of the dashpots and make this quantity tend to infinity. Okay. So, if I take the last spring and I make the viscosity there tend to infinity, basically what we have effectively is a spring. Okay. So, all of the deformations will be taken by the spring and it will be determined from there, right. Similarly, if you want to get rid of the initial instantaneous elastic response, then if you take one of these springs and you can take any of them, because I already took n here, I am taking another case where if you take this term and you make it tend to infinity, then your initial elastic response will be gone and it will be determined by the viscous term, right. So, there are different cases we can do. So, special case. So, let us say I am not sure how many cases we will be able to discuss. So, let us say the special case. So, let eta n tend to infinity. So, let us see what really ends up happening. Okay. So, if you take eta n to infinity, you can redo this entire calculation for that case, or you can take this final equation and you impose the condition that eta n is tending to infinity. So, one of the things that will happen is basically for the last term here, this quantity will disappear 1 by eta n, and you will have the derivative. So, the differential operator acting on f, and on this side you will have again a differential operator acting straight on delta x. A little naive way of thinking would be that the differential operators can be actually be cancelled, but that is not the case. What basically it implies is now you have a simple algebraic relationship between the forces. So, you can actually drop one of these operators. When you drop one of these operators, so this term gets dropped, right. If this term gets dropped, then the power on this side will go down by 1, right. So, at least first thing I can do is I can rewrite the left hand side, and we can say that your left hand side would become, and you have all the other terms, but this is now going to end at n minus 1. Right. And what happens on this other side? The highest power, if you try to redo this, what you will see is the highest power of the differential operator on the other side also decreases by 1. So, it is n minus 1, but now you will also have a constant term, because one of these. So, the way the multiplication and the addition will occur is, then you will have a term which does not have the differential operator, okay. And because you had another E n, you will still have that. If you multiply, these numbers will change. So, essentially what you will have here on the other side, if you rework, is you will have a new set of coefficients and a new polynomial, and I am just going to keep on using q, but I will maybe just put a bar here to distinguish it from the previous q. Sorry, this will now be 0, and then you will have q1 d and all the way, and now the highest power will end at n minus 1. So, this is interesting, and one reason this is interesting is because this side also has highest powers of n. So, maybe I can even write this one as some p 0 plus p 1 d plus p n minus 1 d n minus 1, right. So, this is a very nice ODE, because the polynomials on both sides are very similar. It is only that the coefficients are now going to be different. The powers are the same on both sides, the highest powers. You have all the different terms, and then you also have this other constant term. Okay. So, another case, if you want, so let, instead of the viscosity tending to infinity, what happens if the elasticity tends to infinity? If the elasticity tends to infinity, in the last term here, this particular quantity now disappears, and you have 1 by eta n f n, and that will be equal to this derivative, right. So, basically if you add up all this, then you will again have 1 power less on the left hand side. So, I will add a new page. Okay. So, then your this multiplier basically tends to, because this term becomes negligible. So, your equation becomes, if you rework this whole thing, your equation now becomes, if you retain the factored form, again you will end up with the last differential operator will be of the n minus 1th term, and this is multiplied by f, and on this side you will retain more or less what you had, right. So, you can actually rewrite that as, so the coefficients will now be different than the previous case, the original case. So, maybe I will just put a dash here, and I am just writing this so that here it looks as if it has the same powers. Or I mean, here you can write it in terms of force or the strain, and though we know that they are equivalent. So, we can do that. So, this is strain, this is stress, and that is strain. Okay. So, you will see that here now there is a mismatch of the highest power. On the left hand side, your highest power of the operator d is n minus 1, whereas on this side you have n. Okay. So, let us take this type of a case. So, let us consider an equation of the type P 0 plus P 1 d P n, sorry, okay, this is not legible, Q 0 plus Q 1 d plus all the way till Q n d n, okay, into epsilon. So, we are just considering this type of equation. So, and we have to, let us say, solve them. Okay. Now, there is the jump condition issue will apply here, and you will have to redo the jump condition the same way that we had done it before, right. And that is a very big, quite cumbersome here. So, we will not go into the details of how the jump conditions will work out, but it will be very, very similar to what we had seen before. And the way we will apply it is when we take the Laplace of both sides, and that is what we want to do, just like the previous case. You remember, if you recall the last Laplacian. So, remember this particular problem when we are looking at solving this particular form, and that is why you can see that we are just recasting this previous equation in this particular way. When you take the Laplace of both sides, it's such, it's the initial conditions were such that they cancelled out, right. In our, and then your the whole system becomes such that you are basically taking the Laplace of this particular equation without having to consider the initial conditions. It is almost equivalent to that, right. And so, you here the derivative, whenever you have a derivative, you just have an equivalent s multiplied by that, and that gives you the Laplacian. So, even though we are not going to go into the details of the initial conditions in this particular case, when you do take the Laplace of both on the both sides, then you have a system such that you end up having all those initial conditions cancelled on both sides. So, when you do take the Laplace, so let us say taking Laplace of both sides, you have system such that you have P 0 plus for every differential operator you basically have one s, and this is going to be very nice for us, because what you will essentially end up having is for the nth power of the differential operator, you will have s to the power of n sigma. Now, this is in the Laplace domain. So, I will write sigma bar s, and on this side you will have q 0 plus q 1 again s, the same way till q n d, sorry, not d, that differential operator will become s to the power n, and you will have epsilon bar s, right. And this is such that this particular, so remember that the left hand side can be easily factored, and this is basically your Laplacian of the polynomial now, and I can represent it like this, and this is basically equal to s by E 1 plus 1 by eta 1 s by E n 1 by eta n. And on the right hand side, this is basically equivalent to, this is the Laplacian of the polynomial. Now, q bar, this particular polynomial may or may not be easily factorable, but it is still a polynomial. So, it will have the number of roots, right. So, whether or not it is easy to find the roots is a different question. In this case, the polynomial p can be easily factored, so the roots are very well known. Okay. So, basically what you have is, so or so this form is going to be very helpful for us in solving for the different cases. So, this form is very similar to what we had done before. So, I will just quickly want to show you the similarity with what we had done before, and that should help you understand how the solution process will work. So, remember this is what we previously saw, right. In this particular case, it was simple because the polynomial had only one power of the differential operator, and then things become simple for us, and the same process that we had done can now be repeated for the case of the polynomial with the nth power. Okay. So, what we will do is we will end here, and in the next class we are going to take a look at the solution process and what are the different functional forms of the stress relaxation function, and the creep compliance is something that we will see in the next class. Okay. Okay. So, we will stop here today. Thanks.